Dear Kelly, you and I have never met. I'm not a former SR-71 pilot or RSO. I wasn't a member of your design team at the Lockheed Skunk Works or on the assembly line that built the Blackbird. Nor was I a member of the Air Force at Beale, Mildenhall, or Kadena, who kept the Blackbirds flying. I'm not even an airplane buff in the classic sense. I'm just a person that had the privilege of being around your SR-71 Blackbird, and it was an experience I will remember intensely for the rest of my life. There's just something about your Blackbird, Kelly, that words don't adequately describe. Anyone who has been near a Blackbird and felt its presence knows what I'm talking about. It's a feeling in your gut, and instantly you want to be part of it. Part of what I call the Blackbird family. Today, Kelly, you are being honored for your design work on the SR-71, and justly so. To me, the SR-71 is not only your greatest aircraft design, it is perhaps the greatest aircraft ever built. I've heard it said that you considered the Blackbird the most fascinating challenge of your career. No wonder. It was a design that was so advanced that everything that touched it had to be new. New manufacturing processes, new tools, new materials, a whole new approach. You built an operational stealth aircraft a decade before most of the world had even heard the term. It was a design so far ahead of its time that it retired before time could catch up with it. In times of crisis, the Blackbird provided 6 presidents with a unique and critical view of the world. The Blackbird served this country for just over a quarter of a century. In that entire time, it stood in a class of one. To me, the Blackbird is much more than a technical marvel. It's an airplane that gets inside you, an aircraft that causes the adrenaline to flow just by looking at it. Kelly, your Blackbird is the stuff dreams are made of. It's the model plane sitting in a young child's room, proof that everything is possible, that the sky isn't the limit. And it's the poster hanging on the office wall of a middle-aged engineer, testimony that yes, even in the real world, miracles do occur. The SR-71 embodies all that excites people about aerospace. Its crew seems part pilot, part astronaut. The Blackbird itself appears part airplane, part spacecraft. The typical Blackbird fan is a cross-section of America. It's your grandfather, your niece, your son. It's the wide-eyed young kid that buys an aircraft book at the National Air and Space Museum. It's the family that traveled hundreds of miles to an air show just to see a Blackbird in person. It's the people on the Air Force Base that stopped what they were doing to watch an SR take off. Everyone, every time, no matter how many times they'd seen it before. And it's the pilot who last flew the Blackbird 20 years ago, who has the look in his eye that says, I flew the best aircraft ever made. The look that can barely contain the desire to get in an SR just one more time and light the burners. 972 made its final record-setting flight to Dulles Airport. I watched the television with mixed emotions. This was the Blackbird's final flight. An aircraft that was the very definition of speed and power would fly no more. But my sadness was tempered by the knowledge that this plane would now truly belong to the nation, coming to rest in the Smithsonian National Air and Space Museum. Now millions would be able to do what I had done, be near a Blackbird, be part of the family. Kelly, in the years to come, whenever I want to experience your airplane's majesty, I will remember the time I spent with your Blackbird, the smell of JP7 fuel, the feel of it on the soles of my shoes, the sound of an air starter wind up, the TEB ignite, and I'll put on the film that we shot during those incredible weeks in 1987. I'll watch it, feel it, be part of it again. Because in movies, Kelly, like in our memories, your Blackbird will fly forever. Congratulations, Kelly, and thank you. Devin Hawker, assistant cameraman, Blackbird, the movie.
We knew that, overflying Russia for 4 years, that they were making important advances in radar and missiles. And so in 1958, 2 years before Gary Powers was shot down, we decided we'd try to make a follow-on airplane, which became finally the SR-71, to fly higher and 4 times as fast. So that's the connection between the grandfather type and the SR-71. Then came a number of Mach 3.0 types. The first one of which you'd be familiar would be the YF-12A. Its gross weight is still secret, but the cost performance was excellent. It was a success. Didn't produce any because there wasn't any threat. Not until the backfire bomber showed up.
Of the many aircraft whose origins can be traced back to Lockheed's renowned Skunk Works, none is more significant than the A-12. More than any other aircraft, this titanium masterpiece represented the apex of aeronautical engineering in its day, not only at Lockheed, but at every significant aerospace engineering bureau around the world. Today, over 3 decades after its first flight, it remains the aircraft by which all others are judged. Project Suntan had given Kelly Johnson and the Lockheed Advanced Development Team engineers a significant opportunity to explore the attributes of hydrogen propulsion systems. Equally as important, however, Suntan also permitted the exploration of advanced airframes, optimized for the first time to cruise at speeds well in excess of Mach 3. Soon after the U-2's first flight during 1955, Richard Bissell moved quickly to organize the research and development of follow-on systems, including what was to become the A-12. New studies, conducted under the codename Gusto, were initiated exploring the design and possible development of a totally new subsonic reconnaissance platform that would be designed from the start to incorporate the lowest RCS obtainable. The resulting analysis concluded that supersonic speed, coupled with the use of radar-attenuating materials and radar-attenuating design considerations, greatly reduced the chances of radar detection, though it did not reduce it to zero. Lockheed Aircraft Corporation and the Convair Division of General Dynamics during the fall of 1957 were to respond to a general operational requirement calling for a high-speed, high-altitude reconnaissance aircraft, but to do so without a formal contract or government funding. Johnson spent virtually every available minute working on the advanced aircraft program, which he sometimes jokingly referred to as the U-3. Project Gusto now was terminated, and a new codename, Oxcart, was assigned. Ben Rich would note that the A-12 was composed of 85% titanium and 15% composite materials. Learning to work with titanium proved to be a major undertaking. The myriad breakthroughs pioneered by the Skunk Works manufacturing team in conquering this metal remain one of the great and unheralded successes of this most incredible program. Just a great deal of work with the many problems we have trying to get this airplane built. Everywhere you turn, there are tremendous problems requiring invention, new systems, and money. An official first flight with appropriate government representatives on hand now was made on April 30th. Nearly a year behind schedule, the aircraft became airborne for the first time. With Lou Schulk at the controls, the aircraft lifted off at 170 knots. The landing gear was retracted and a climb was made to 30,000 feet. A top speed of 340 knots was reached during the flight, which lasted for 59 minutes. Following an uneventful landing, Schulk expressed satisfaction with the aircraft's stability and the way it handled. On the second flight, on May 4th, the A-12 went supersonic for the first time, reaching Mach 1.1. Problems were minimal, and Johnson began to feel confident that the flight test program would progress rapidly, possibly recovering some of the time that had been lost in the drawn-out manufacturing process. The Cuban Missile Crisis now reinvigorated the program. The loss of Major Rudolph Anderson's U-2 over Cuba on October 27th underscored the increasing vulnerability of this subsonic platform when operating in denied airspace, and this was not lost on intelligence community offices involved with the overflight program. At the end of 1962, 2 A-12s were in flight test. one powered by J-75s and the other powered by one J-75 and one J-58. A speed of Mach 2.16 and an altitude of 60,000 feet had been achieved. Flight test progress was still slow, and the engine delays and thrust deficiencies remained a major concern. Meanwhile, by the end of 1963, the CIA's A-12 flight test program had resulted in 573 flights, totaling 765 hours. 9 aircraft were on hand at the test location. It should be noted at this point that on July 24, 1964, President Johnson made the first official announcement concerning the forthcoming Lockheed SR-71. With the A-12 situation vacillated back and forth between an operational commitment and continued wait-and-see, flight testing of the YF-12A had continued. During July of 1966, Johnson wrote in the log, "We were directed to give up further flying of the YF-12As, although we had proposed shooting down a drone at Holloman to get the effect of ground clutter for low-altitude targets." The following August 5th, he wrote, "We've laid off half of our test crew on the YF-12A and are maintaining only enough people to store the airplane or send it to Burbank. We are very near the end of this program." As late as January 26, 1967, Johnson made the following comments in the A-12 log. "We jointly agreed there would be just one round and not two. That seems to have been a very accurate evaluation, as it seems that 30 SR-71s give us enough overflight reconnaissance capability, and we don't need the additional 10 A-12 aircraft." On January 5, 1968, an official wire closing down the F-12B was received from the Air Force. The YF-12A program would be formally ended on February 1st. In a final disheartening move, the Air Force, on February 5th, sent Johnson a letter instructing Lockheed to destroy the A-12 F-12 tooling. The final A-12 flight took place on June 21st, 1968, when the last remaining aircraft, number 131, was ferried from the test location to Palmdale by CIA pilot Frank Murray and placed in storage. It would remain there for the following 2 decades. On June 24th, Johnson wrote, "While the intelligence community in Washington wanted very much to keep the A-12 program going, the present financial situation cannot stand the strain. It's a bleak end for a program that has been overall as successful as this." In summary, the A-12 program lasted just over 10 years from its inception during 1957 through its termination during 1968. The Skunk Works produced 15 A-12s and 3 YF-12As. 5 A-12s and 2 YF-12As were lost in accidents. 2 pilots were killed, and at least 6 had narrow escapes. In addition, 2 F-101 chase aircraft were lost with the Air Force pilots during the A-12 test program. The main objective of the program, to create a reconnaissance aircraft of unprecedented speed, range, and altitude, was triumphantly achieved. It may well be, however, that the most important aspects of the effort lay in its byproducts, the notable advances in aerodynamics, engine performance, cameras, electronic countermeasures, pilot life support systems, and the arcane art of milling, machining, and shaping titanium. Altogether, it was a pioneering accomplishment, almost certainly never to be repeated in the history of aviation. The YF-12A developed into the SR-71, and in that case, again, the cost performance was excellent as we gave back to the government well over $19 million on the contract, and we consider it to be a success. On December 6, 1962, Kelly Johnson noted in his log, "Working on R-12 Universal Airplane using company work order. Can get no decision on any military version of the aircraft, but there does seem to be considerable interest in it." Johnson's rationale for this design was based on the premise that if he produced a single platform capable of performing the reconnaissance, recon strike, or intercept role depending on customer needs, it would greatly simplify production, and it eliminates the necessity of the Air Force deciding which version they want to buy. 7 days later, the Skunk Works was visited by several SAC personnel, and Johnson logged that they wanted to see what kind of a reconnaissance version would meet SAC's needs. We prepared our proposal for a 140,000-pound reconnaissance airplane capable of carrying 4,300 pounds of reconnaissance gear and gave it to Colonel Templeton with a forwarding letter. By March 18, 1964, R-12 construction was moving along with considerable rapidity, but contract negotiations had yet to be concluded with the Air Force. Johnson noted in the log, "Spent several days on the first 6 R-12s. It is extremely difficult to get a reasonable profit for what we do, and no credit is given for the fact we operate more cheaply than others." All activity relating to the R-12 and RS-12 configurations had, of course, been kept completely under wraps in the Skunk Works and within the confines of the involved Air Force and CIA offices. On July 24, 1964, however, President Johnson made his memorable announcement revealing to the world the existence of Lockheed's Mach 3-capable reconnaissance aircraft. "I would like to announce the successful development of a major new strategic manned aircraft system which will be employed by the Strategic Air Command. This system employs the new SR-71 aircraft and provides a long-range advanced strategic reconnaissance plane for military use, capable of worldwide reconnaissance for military operations. The Joint Chiefs of Staff, when reviewing the RS-70, emphasized the importance of the strategic reconnaissance mission. The aircraft will fly at more than 3 times the speed of sound. It will operate at altitudes in excess of 80,000 feet. It will use the most advanced observation equipment of all kinds in the world. The aircraft will provide the strategic forces of the United States with an outstanding long-range reconnaissance capability." In August 1964, Kelly Johnson phoned Bob Murphy and asked him if he wanted to work on the new reconnaissance aircraft. At the time, Murphy was a superintendent in charge of D-21 drone production. He accepted the offer and was immediately briefed by Johnson, who said, "I want you to go to Palmdale and get Site 2 away from Rockwell. Hire the people you need. The pieces of the aircraft will be up with you on November 1st, and I want her flying before Christmas." The SR-71 was 107 feet, 5 inches long, had a wingspan of 55 feet, 7 inches, and a wing area of 1,605 square feet. It stood 18 feet 6 inches high to the top of the rudders, and its gross weight varied from 135,000 pounds to over 140,000 pounds. The effect of thermodynamic heating brought about by the aircraft's extreme operating envelope was a major factor affecting its construction. Fully 93% of the airframe was built from titanium, while the remaining 7% consisted of laminates, of phenylsilane, silicone, asbestos, and fiberglass to help reduce the aircraft's RCS. The SR-71's forward fuselage has a circular cross-section and is of semi-monocoque construction. It housed the pilot and a reconnaissance system operator, RSO, seated in tandem, the front undercarriage, fuel cells, and the air refueling receptacle. The delta wing features 2 prominent engine nacelles, each mounted at mid-semispan and blended into the wing to further reduce RCS. 2 rudders mounted on top of each nacelle and canted inboard 15 degrees from the vertical also reduced the aircraft's radar signature. A large aft-moving spike extends forward from each nacelle, which helped to regulate mass airflow to the 2 Pratt & Whitney J58 engines. The maximum fuel load weight for the SR-71 was 80,280 pounds, and it was carried in 6 fuel tanks. Built to cruise in afterburner at Mach 3.2 and at altitudes in excess of 80,000 feet, the aircraft encountered extremely high airframe temperatures generated by thermodynamic heating. This, coupled with the diverse operating envelope of its Pratt & Whitney J58 engines, required the development of a special fuel which served not only as the source of propulsive energy, but also as a hydraulic fluid optimized in the engine hydraulic system to activate the main and afterburner fuel nozzles. On the ground, the aircraft was only half filled with fuel, and then pressurized using LN2 to 1.5 psi above ambient pressure. Shortly after takeoff, the SR-71 would rendezvous with a tanker and get topped off. The Air Intel control system was a major innovation used to exponentially increase the speed performance of all Kelly Johnson's so-called Blackbirds. At Mach 1.4, the outlet doors located in the exterior of the engine nacelle began to modulate automatically in order to obtain a prearranged ratio between dynamic pressure outside the inlet throat and static duct pressure inside the inlet cowl. At 30,000 feet, the inlet spikes unlocked and, at Mach 1.6, began moving rearward, achieving their fully aft position at Mach 3.2, design cruise speed. Cruising covertly during operational missions at speeds in excess of a mile every 2 seconds, it was essential that the SR-71's navigation system was both highly accurate and not reliant upon external navigation aids to ensure the aircraft remained on the black line. At the heart of successful mission accomplishment, therefore, was the Nortronics Astro-Inertial Navigation System, or ANS, designated NAS-142V2. Originally designed for the Douglas Skybolt air-to-surface ballistic missile, which was canceled in 1963, it proved to be a perfect solution for navigating the SR-71 after a few modifications and updates. The system combined data from the inertial navigation platform with a time datum accurate to within 5 milliseconds. Position updating was achieved automatically by astro-tracking at any one time 6 of the 52 most prominently visible stars by day or night, in effect using nature as a global positioning system long before GPS was developed. When the autopilot was coupled to the ANS via the auto-nav function, the SR-71 could be flown automatically, adhering precisely to a predetermined flight path that was loaded pre-flight into the ANS's computer memory. To facilitate maximum mission flexibility, the SR-71 featured 3 interchangeable nose sections, housing either a high-resolution, side-looking radar, used for ground mapping and referred to as CAPRI, standing for Capability Reconnaissance Radar, an advanced synthetic aperture radar system, or ASARS, or a so-called glass nose housing a palletized optical bar camera, or OBC. The SR-71 did not carry any form of defensive weaponry save that which was generated electronically. ECM was and remains a highly sensitive area, where fast-moving technological advances meant that the SR-71's defensive electronic systems required continual updating throughout its operational life. Within the SR-71's cockpit, pressurization was allowed to fall steadily as the aircraft climbed from sea level to 8,000 feet, whereupon it remained constant to 25,000 feet. This ensured that the fuselage wasn't subjected to unduly high pressure gradients, which in turn meant that the aircraft's structural weight could be reduced. However, if pressurization was lost or the crew needed to eject, survival was dependent upon each of them wearing a full pressure suit. This requirement was reinforced by Air Force Regulation 60-16, which stipulated that full pressure suits must be worn when flying above 50,000 feet. In 1977, the company developed the next generation of pressure suits, designated the S-1030 series, and featured a high level of commonality between the U-2 and SR-71 programs. Colored old gold, the suit incorporated state-of-the-art textiles and was more durable and comfortable. Its 4 principal layers consisted of an outer coverall of Nomex that was durable, tear, and fire-resistant. The helmet, designated GN121394, was attached to the suit via a rollerball ring to enable the head to be turned. Oxygen was supplied to the crew members through holes situated around the helmet face seal. An airtight port located on the lower right side of the helmet enabled crew members to drink water via a straw to ensure they remain hydrated, and a level of sustenance was also available in the form of liquidized food dispensed from a tube. Gloves completed the pressure seal and were attached via wrist hinges. Boots featured heel retraction strips that were connected by cable to the ejection seat on entry to the cockpit. The complete pressure suit system cost about $130,000 a copy. Crews were issued with two, and they lasted 10 to 12 years, undergoing a complete strip-down overhaul every 5 years and a thorough inspection every 90 days, or 150 hours. December 22nd. The first SR-71, with SkunkWorks test pilot Bob Gilliand at the controls, took to the air for the first time. Departing from Lockheed's Air Force Plant 42, Site 2 facility at Palmdale, it remained airborne for just over an hour and reached a speed in excess of 1,000 miles per hour, which, Johnson noted, is some kind of record for a first flight. Though the SR-71 first flight had been completed with few difficulties, ongoing flight testing of the aircraft had not been comparably problem-free. The SR-71 flight test program, conducted at Palmdale, like that of its A-12 predecessor, was not without its accidents. The first, involving the third SR-71A, occurred on January 25, 1966, when SkunkWorks pilot Bill Weaver miraculously escaped without using his ejection seat. His back sealer, Jim Zwire, was not so lucky and was killed. At the time of the accident, the aircraft was in a right turn, and the right inlet forward bypass doors were being controlled manually by Weaver. Though SR-71s finally were beginning to enter the operational Air Force inventory, the miscellaneous subsystem problems remained difficult to overcome. Tank sealing and range deficiencies continued to plague the aircraft, including those considered operational at Beale Air Force Base, and corrective action was painfully slow in overcoming them. By late 1967, all 31 SR-71s on order from Lockheed had been completed and delivered. By late September of 1969, the SR-71 was well on its way to a long and illustrious operational career. SAC already had flown well over 100 hot missions out of Kadena. NASA, for the first time, formally inquired into having an SR-71 for test purposes on December 29, 1970, when a query was received by the Skunk Works concerning possible use of the aircraft to launch test-scale models of the forthcoming space shuttles. On July 28, 1971, Johnson noted in the log, "Nothing new on the SR-71 operation. SAC made a 10-hour flight a short time ago on which about half the time was over Mach 3 and 80,000 feet. They flew 10,000 miles. The Vietnam War had successfully justified the SR-71's existence from the time of its operational debut during 1968 through 1973. Some 600 missions had been logged during the course of Vietnam operations, and the aircraft had logged an enviable record of dependability and mission successes. Temporary deployment to forward operating locations, or FOLs, worldwide were undertaken with considerable alacrity, and during the course of its service career, the aircraft overflew almost every major political and military significant hotspot in the world, gathering intelligence data of inestimable political and military value. The previously mentioned YF-12A speed and altitude records were eclipsed by the SR-71A during a series of Fédération Aéronautique International monitored flights during 1976. As of this writing, all of these records still stand, including the world's absolute speed and sustained altitude records. During the late 1980s, as major international political and economic changes began to manifest themselves throughout the world, the U.S. intelligence community began to reassess priorities and, in particular, the way it was going to spend its limited financial resources. Virtually every program, including the SR-71, was reviewed with the intent of determining its long-term viability and, in particular, its simple cost-effectiveness. As a result of this review, and in light of advances in other sensor system programs, on October 1, 1989, all SR-71 activities, with the exception of crew proficiency training and associated training flights, were suspended while the Air Force awaited release of the 1990 fiscal year budget. When revealed several weeks later, funding for the SR-71 program had been eliminated. Accordingly, all Air Force SR-71 operations were terminated officially on November 22nd.
Good evening. Recent budgetary cuts for the Air Force have ended funding for the SR-71 Reconnaissance aircraft program. Local civilian and military personnel had the opportunity to view the final functional check flight of the SR-71 as it prepared to return to the United States.
Rolling down Kadeena's runway for one of the last times, the SR-71, nicknamed the Habu, performed a functional check flight in preparation for its last trip to the United States and into the pages of history. The atmosphere was charged with excitement as the flight crew, Major Jim Greenwood and Captain Steve Zaviniak, were assisted into 45 pounds of pressure suit. The physiological support technicians then conducted pressure tests on each suit and again performed these tests in the aircraft during pre-flight. The extra tests help ensure the suits will work in the event the pilots need to eject. The suits allow ejection at altitudes above 80,000 feet at speeds of Mach 3. After all pre-flight checks were done, the engines were started and the Habu came to life and soared into the skies of Okinawa for one of the last times. From Kadena Air Base, I'm Airman Rob Ivy.
Many of the Lockheed, Air Force, and CIA personnel who had been involved in the program during the preceding 24 years were on hand to say farewell to what many viewed as the single most significant military aircraft of the post-World War II period.
Everyone called him Kelly, and as he reminisced that day about the genesis of his Mach 3 masterpiece, he could have just as easily reflected back on a time when aircraft designers were striving for 200 miles per hour, a time when he landed his first job with the fledgling Lockheed Aircraft Company. In 1932, a small group led by Robert E. Gross had purchased Lockheed out of bankruptcy for $40,000 and staked the company's future on the development of an all-metal, twin-engine transport. Models of the design were sent to the University of Michigan, where a young graduate student named Clarence L. Johnson conducted wind tunnel tests. Although his faculty advisors gave the design a passing grade, he wasn't much impressed, and after he had been hired on as a tool designer at Lockheed in August of 1933, he let Chief Design Engineer Hal Hibbard know about it. Among other things, it'd be directionally unstable, especially with one engine out. A rather presumptuous and certainly unconventional way for a 23-year-old to start his career with a new company, but it was only a hint of what would follow. The son of Swedish immigrants, he'd been nicknamed Kelly by classmates because of his quick temper, stubborn tenacity, and unwillingness to back down from a fight, even against overwhelming odds. Instead of reminding the outspoken young man of his place, Hibbard suggested he go back to the wind tunnel and see if he could improve the design. After 72 test runs, he came up with the solution, an unconventional twin-tail arrangement soon to become a Lockheed trademark. And the Model 10 Electra became the foundation for Lockheed's future growth as various models of the airplane helped revolutionize commercial air transport in the 1930s. With his work on the design, Kelly Johnson became the sixth member of an engineering department in an industry which then couldn't afford specialists. working often simultaneously as an aerodynamicist, stress analyst, weight, wind tunnel, and flight test engineer. He also put in long hours out in the shop, getting hands-on production experience and learning firsthand the importance of designing producibility into an airplane. It was a real-world education on all phases of design and development that within a decade couldn't be duplicated, and the lessons learned became guideposts for the rest of his career. He flew, for example, as flight test engineer on all models of the Electra, and worked for some of the most notable figures in aviation, such as Amelia Earhart. Out of this experience came his lifelong conviction that the designer had to be able to test his own airplane. As he later commented,
And I decided at an early age that unless I had hell scared out of me once a year, I wouldn't have the proper balance to really design a new airplane of any type.
Kelly Johnson would log more than 2,300 hours as a flight test engineer. The versatile Electra spawned two major developments. One was the XC-35, a modified Model 10, which in 1937 first demonstrated the practical feasibility of transforming the entire fuselage into a pressurized cabin to permit comfortable high-altitude flight. Johnson was Lockheed's flight test engineer on this project, gaining first-hand experience with the problems of pressurization, and more important, with the tremendous possibilities pioneered by this aircraft. Possibilities to which he and Hall Hibbard began to give serious consideration. Meanwhile, the Model 14 Electra incorporated a number of Johnson innovations, such as the first practical application of Fowler flaps, which both increased the wing's lifting surface and served to permit slower, shorter distance landings, an achievement which won him the 1937 Lawrence Sperry Award. In 1938, the high speed and innovative features of the Model 14 attracted British interest in its potential as an anti-submarine patrol plane. But the requirements necessitated a major redesign. Johnson worked around the clock for 3 days to transform the Model 14 into the Hudson bomber. The British ordered an initial batch of 250 aircraft, at that time the largest production order ever received by an American company. But there would be many more, 2,000 to the RAF alone, out of a total production run of nearly 3,000 airplanes. The Hudson put Lockheed into the big time. But even as production was gearing up, Kelly Johnson and his colleagues were well into other much more ambitious designs. The success of the pressurized XC-35 and the recognition that the next generation of air transports would be much larger, higher-speed, transoceanic aircraft inspired Johnson, Hibbard, and a small design team to lay out the now classic lines of the Model 49 Constellation in 1939. Using his soon-to-be legendary powers of persuasion, he convinced Lockheed to build its own wind tunnel, a decision that paid for itself many times over during the development of this design, as all aerodynamic problems were overcome early on, and not one external change had to be made to the actual aircraft. Hibbard was so impressed by Johnson's wizardry that he swore he could see air. Commercial development of the legendary Connie would be delayed by the war, and it first flew as the Army Air Force's C-69. This, however, provided time to refine the airplane so that at war's end, Lockheed was postured to capture a lion's share of the commercial market, and various models of the elegant Connie would continue to grace the world's airways into the late 1950s. At the time he laid down the basic design of the Constellation, Johnson was already well into another path-breaking project. In early 1937, responding to an Air Corps requirement for a high-altitude interceptor capable of 360 miles per hour, Johnson and Hibbard hastily conceived some possible configurations, depicted here in one of Kelly's rough sketches. As Johnson observed many times, in design, you're forced to develop unusual solutions to unusual problems. Their decision to go with an unconventional twin-boom configuration was dictated by another axiom. Design features are the creatures of necessity. The twin booms evolved as a logical development of engine nacelles which had to be extended to house the liquid-cooled engines, turbo superchargers, radiators, and main landing gear. It seemed logical, then, to simply extend the nacelles into booms which could carry the empennage. Their novel approach produced a winning design, and when the XP-38 was finally rolled out in January of 1939, its sleek lines bespoke speed. And when Lieutenant Ben Kelsey took it up for its maiden flight, it delivered an impressive 403 miles per hour, far exceeding the requirements. Thus began the saga of the P-38 Lightning. The first American aircraft able to fly at such speeds, it offered dazzling performance and a host of new problems. For as it peeled over into dives at high altitudes, it could hit speeds approaching 500 miles per hour. In this region, the aircraft began to violently shake and nose over into increasingly steeper angles, and control forces became so heavy pilots couldn't pull out. Tragically, some never recovered. Kelly Johnson wasn't taken by surprise. Although many insisted it was tail flutter, he immediately recognized it as the then little understood phenomenon of compressibility. At 500 miles per hour, localized airflow over certain parts of the aircraft was reaching supersonic velocity, and this produced shock waves and serious problems. The P-38 was the first aircraft to encounter this, and so little was actually known about it that Johnson launched exhaustive wind tunnel studies and an accelerated dive test program headed by Chief Test Pilot Milo Burcham. After more than 2 years, he finally identified the problem as shock stall in the wing, which reduced lift and increased drag, thereby inducing the nose-down tuck. Typically, he was quick to devise a cleverly simple remedy: a dive flap mounted to the main wing spar that, when deployed, generated a positive pressure field, immediately restoring lift and a nose-up pitching moment. Flown on every battlefront, the P-38 excelled in combat. Christened the fork-tailed devil by Germans, the versatile fighter, combining speed and load-carrying capability, proved adaptable to a wide array of combat roles, and its long legs made it ideal for the vast reaches of the Pacific, where it destroyed more enemy aircraft than any other Allied fighter. Impressive though it was, Kelly Johnson was never satisfied with it. He'd long foreseen the inherent limitations of prop-driven aircraft, and though unaware of developments in Germany and England, where turbojets had already been successfully developed, he decided that props had to go. Thus he and Hibbard became the first in this country to seriously pursue the possibilities of turbojet propulsion, when in 1939 they asked Nathan Price to design an experimental turbojet power plant. Design of the L-1000 got underway in 1940, and by 1942, Price had come up with a truly advanced design, a high compression ratio, twin spool, axial flow power plant promising an extraordinary 5,100 pounds of thrust. Meanwhile, Johnson and a young engineer named Willis Hawkins led a design team that came up with the L-133, a truly radical twin-engine stainless steel aircraft featuring thin wings and canard surfaces, and projected to achieve 625 miles per hour at 50,000 feet. But surprisingly, when Johnson submitted a proposal for development of the engine and airframe in March 1942, the Army Air Forces showed little interest. Although launched long after his effort, top-secret development of an American turbojet fighter powered by a British Whittle engine was by then already underway. The Bell XP-59A first flew at Muroc Army Air Force Base on California's high desert in October of 1942, but it proved to be underpowered, overweight, and scarcely optimized for jet flight, and early on, the Army Air Forces decided that it wouldn't meet frontline fighter requirements, though Bell didn't yet know this, and the testing continued. On June 10, 1943, a Bell engineer at Muroc reported back that Johnson had been permitted to examine the still top-secret XP-59A, and he wondered what he was up to. Unbeknownst to Bell, The Army Air Force had already asked Lockheed to submit a proposal for a simpler, single-engine jet fighter built around a 3,000-pound thrust Halford H-1 engine, which would be capable of frontline service. Johnson took in a lot that day, but he'd already been wrestling with jet propulsion for nearly 3 years, and he already had a suitable design well in hand. When he made his proposal at Wright Field on June 18th, he made the astounding promise that he'd deliver an aircraft within just 180 days. Getting immediate approval, he was cautioned that the utmost secrecy was required. Lockheed was already swamped in terms of manpower, tooling, and facilities with wartime contracts. But this was a blessing in disguise, an opportunity to implement an idea he'd been pestering Robert Gross about for years. Let him round up a small group of talented people, designers, engineers, and shopmen, put them under one roof where they could all work closely together, and give him complete authority over everything from procurement to flight test. With no other options, Gross said, "Go ahead." Stealing people from around the plant, just 28 engineers, including himself, and 105 shopmen, he also built a small facility out of discarded shipping crates, using a circus tent for a roof. On June 19th, he laid down the principles under which the project would operate. In 1.5 pages, now preserved on old photostats, they formed the basis for how he'd try to operate for the next 30 years. He'd be responsible for all decisions. Paperwork and red tape would be cut to the minimum. Each engineer would be designer, shop contact, parts chaser, and mechanic, and each would remain within a stone's throw of the shop at all times. There'd be but one object: to get a good airplane built on time. The daily log indicates that 2 days later, he laid out the horizontal structure of the organization. No pyramidal, multi-tiered layers of management. Each project engineer and the shop foreman would report directly to him, and in fact, he'd be looking over everyone's shoulder. He wanted information direct from the men doing the work, and if they had questions, they'd get decisions immediately on the spot. He'd promised the airplane in 180 days. As would become his custom, he gave his men 150. The clock started ticking on June 23rd. Forcefully reminded that simplicity is the keynote of good design, the designers jumped into their work. But this was a new kind of operation, and instead of moving from stage to stage, the schedule demanded an extraordinary degree of concurrency. With finished detailed design still many weeks away, the mock-up was started on June 30th and completed by July 17th. By then, milling and fabrication of parts and the construction of jigs to assemble a prototype was already well underway, and by July 31st, the bulkheads were going into the jigs. And section by section, the airframe started coming together. Throughout this period, however, the design process continued. As concurrent wind tunnel tests revealed problems, the wing and the engine air inlets were the biggest headaches. He'd gambled on the wing, a laminar flow airfoil that had never before been tested on an airplane, and of course, nobody had had any experience with inlets. Johnson was willing to accept mistakes on such an accelerated and risky venture, as long as they were reported promptly. Typically, he never asked why, but what are you going to do to fix it? The project was so secret that his group didn't even have a name. The whole setup reminded one of his design engineers, Irv Culver, of the mysterious place where Hairless Joe, one of Al Cap's cartoon characters in Little Abner, ground up skunks, old shoes, and other unsavory ingredients to brew a potent concoction called Kickapoo Joy Juice. So inspired, he answered the phone one day, "SkunkWorks, Inside Man Culver." Though Johnson wasn't amused, his organization suddenly had a name that stuck. Remarkably, the completed aircraft arrived at Muroc on November 14th, just 143 days after startup. But when the engine was run up 3 days later, there was a terrific roar as the inlet ducts collapsed, sending debris into the engine and cracking the impeller. It took 6 weeks to get a new engine, but on January 3rd, 1944, Milo Burcham successfully completed the taxi tests. And 5 days later, in the chill of the morning on January 8th, Johnson, in white coveralls, overcoat, and stocking cap, worked intently with his crew preparing for the first flight, as over 100 SkunkWorks employees stood atop a hill looking on. He wanted everyone who'd worked on the airplane they now call Lulu Bell to be on hand. He told Burcham, "Just fly her, Milo, and find out if she's a lady or a witch." At 9:15, he took off. But only 5 minutes later was taxiing back to report that the landing gear hadn't retracted and that the boosted ailerons felt too sensitive. While the gear problem was being fixed, Johnson assured him that the control sensitivity was normal, and at 10 o'clock he took off again, and this time put on a dazzling 20-minute display, attaining a top speed of 490 miles per hour and reporting a roll rate of 360 degrees per second. Back on the ground, he was able to report that Lulu Bell was indeed a lady. The XP-80 ultimately became the first American aircraft to exceed 500 miles per hour, but this was only the beginning. For months, Johnson had been working on a larger, more advanced version with a 4,000-pound thrust General Electric I-40 engine, promising much greater speed. He promised the XP-80A in just 150 days and delivered it in 132. But as Tony LeVere taxied in after the first flight on June 10th, he'd had a few surprises. Center of gravity miscalculations had caused porpoising. A faulty pressurization valve had channeled 325-degree engine bleed air into the cockpit, and malfunctioning flaps put the airplane into violent rolls. Only his superb flying skills allowed him to bring it back, and Johnson was so grateful he doubled LeVere's bonus, a gesture pointing up the special relationship between them, and indeed between Kelly Johnson and all of his test pilots. Unlike so many of his peers, Johnson both understood and appreciated what his pilots did. He flew with them whenever possible, shared their concerns, always listened, and then acted on their recommendations. The XP-80A's problems were quickly remedied, and it went on to become the prototype for America's first operational jet fighter. Though it wouldn't enter combat in World War II, the P-80 Shooting Star would deliver awesome performance. In January of 1946, for example, Colonel William Council completed the first non-stop transcontinental jet flight covering 2,450 miles in a record 4 hours and 13 minutes at an average speed of 580 miles per hour. In June of 1947, flying a specially modified P-80R, Colonel Albert Boyd completed 4 runs over a speed course at Muroc, averaging 623 miles per hour, and reclaiming the world speed record for the United States for the first time in 24 years. And over Korea in November of 1950, a Shooting Star would down a MiG-15 in history's first all-jet combat. And amply confirming Johnson's methods and his insistence on simplicity, the P-80 would give birth to a number of progeny. Shrewdly sensing the need for a jet trainer, Johnson gambled $1 million of Lockheed money on the development of an F-80C airframe into a 2-seat configuration, which after its first flight in March of 1948 was transformed into the classic T-33, an airplane affectionately called the T-Bird, which would serve as the standard jet trainer for legions of student pilots around the world for the next 3 decades. In response to an urgent Air Force requirement for an interim all-weather interceptor, the T-33, in turn, served as the basis for 3 different models of the F-94 Starfire, which filled a critical void, while newer designs specifically tailored for that role remained under development in the early 1950s. Not done yet, the now vintage design would realize its final incarnation as the T-2V1 Sea Star, an advanced, navalized version of the T-33. All of the iterations of the P-80 design were still yet to come, however, as in 1946 he started design work to meet an Air Force requirement for a new penetration escort fighter. Early on, he explored the possibility of applying new concepts, a delta wing, even in-flight variable wing sweep, and then discarded both, some of the more than 60 concepts he'd examine and reject. When the XF-90 finally rolled out, 3 years later, it was the victim of ever-changing and conflicting requirements, from a time to climb of 35,000 feet in 10 minutes to 50,000 in 5, 900-mile range to 1,500, and then back to 600, and finally ground attack capability in a high-speed, high-altitude design. This prompted him to build a brawny airframe, over 30,000 pounds fully loaded, and stressed for over 12 Gs. When Tony LeVere took off on early test flights, he had to use rocket assist because the pair of small 3,000-pound thrust J-34s still lacked afterburning capability. The usual post-flight congratulations and festivities belied the fact that Johnson knew he was facing terrible odds. With the same pair of inadequate engines as their principal rival, the McDonnell XF-88, yet half again as heavy because the 88 hadn't been beefed up for ground attack, Johnson's airplane was bound to suffer performance-wise. It was overweight and underpowered, and even when afterburning was finally added, boosting combined thrust up to more than 8,000 pounds, its top speed and level flight was only 668 miles per hour, slower than existing operational F-86s. It achieved one distinction, however, when in April 1950, LeVere pushed over into a steep dive, and it became the first Lockheed airplane to exceed the speed of sound. With performance no better than the XF-90s, the McDonnell entry won the competition, but neither design went into production. The whole ordeal taught Johnson never again to take on a job unless the requirements were both well-defined and firm. Even though a failure, the XF-90 went on to demonstrate that he certainly knew how to build a rugged airframe, as in April 1952, it survived the first of a series of atomic blasts, suffering only 20 hours worth of repair work. Meanwhile, Johnson was completing work on a much more unconventional airplane. Designed to meet a Navy requirement for a vertical takeoff and landing, or VTOL fighter, the XF-V1 was supposed to claw its way straight up by means of huge contra-rotating props driven by a twin turbine power plant, providing more power than the airplane's weight. Engine development lagged, however, and after test pilot Herman Fish Salmon first lifted off from the lake bed at what was now called Edwards Air Force Base in December 1953, the underpowered XF-V1 continued to rely on its makeshift landing gear for all takeoffs and landings. Once aloft, however, Salmon was able to demonstrate that it could make satisfactory transitions from horizontal to vertical flight, and that it could hover in the vertical attitude. But, lacking the promised power, and explaining in his words that it's awful hard to fly an airplane looking over your shoulder, Salmon wasn't eager to attempt vertical liftoffs or touchdowns. Neither was Johnson, who, believing a designer shouldn't be afraid to fly his own airplane, had the integrity to recommend cancellation of the whole project. By that time, however, he already had a much more promising design on the ramp at Edwards. When Tony LeVere first saw it, he asked incredulously where the wings were. But those tiny, blade-thin wings and everything else about the XF-104 were actually the product of years of careful thought, effort, and Johnson's determination this time to employ his SkunkWorks methods. Back in 1947, he'd modified a P-80 with wingtip-mounted ramjets, and with Fish Salmon at the controls, it became the first piloted aircraft to fly on ramjet power alone. These tests supported a major Skunk Works type of effort to explore a whole new realm. At a time when missile and guidance system technologies were still in their infancy, Johnson's team had to design a pilotless Mach 3 testbed to further explore ramjet technology. The X-7 was the product of their efforts, and its tiny, thin, slightly tapered wings, Johnson's solution to the problems of high Mach flight, has been thoroughly tested on rockets and with scale models. The X-7 first flew in April 1951 and went on to a remarkable career. Launched from a B-29, boosted to high speed by powerful rockets, and then flying on various ramjets under test, it ultimately exceeded Mach 4 and climbed well above 100,000 feet. Thus those small, thin wings were already more than just a theory when Johnson visited the Korean battlefront in 1951. Still smarting from the XF-90, he'd gone there to talk to the ultimate customers, combat pilots, about what they wanted in a fighter. To a man, it was higher speed, more altitude, and less complexity. Intent on giving them just that, he made an unsolicited proposal to build a fighter for which no requirement yet existed. When he promised Mach 2 and 60,000 feet in a simple, lightweight fighter, Colonel Bruce Holloway stepped into the next room and within 2 hours returned with a short 1.5-page list of requirements. This time, with a firm, straightforward requirement, Johnson returned to his favorite Skunk Works mode of operation, and less than a year later, in February of 1954, Tony LaVere lifted the XF-104 from the lake bed for its first flight. Though configured with a much lower thrust engine than the powerful J-79 scheduled for the production model, the XF-104 was still faster than any other fighter in the world. But Johnson had produced more than just a dazzling performer. Fanatical about costs and producibility, while design of the prototypes was still underway, he'd set up a small group of engineers to find the cheapest and most efficient way to produce each part of the production airplane, an innovation which would result in savings of about $12,000 per aircraft and millions for his customers. When the press finally got to see the F-104, they called it the missile with a man in it, and they weren't far off the mark. The first Mach 2 operational aircraft in the world, it would go on to shatter every significant record on the books. 91,000 feet and 1,400 miles per hour in May of 1958, making it the first aircraft ever to hold both the world altitude and speed marks simultaneously. 3 time-to-climb records later that year. And in 1959, it became the first airplane taking off on its own power ever to climb above 100,000 feet, as Captain Joe Jordan zoomed up over 103,000 feet. This kind of performance clinched the 1958 Collier Trophy for Johnson. While the Starfighter was capturing headlines with record-breaking performances, another, much more exotic Johnson design was unbeknownst to all but a few, almost daily cruising in level flight at altitudes far beyond any official records. It had been born of the massive arms buildup of the early 50s, when U.S. intelligence agencies urgently needed confirmation of reports of major Soviet advances in intercontinental range bombers and ballistic missiles. The decision to proceed with overflights led to a design competition for a reconnaissance aircraft capable of 70,000 feet. Though Lockheed hadn't been invited to participate, Johnson had caught wind of it and hastily submitted a proposal to build the CL-282, essentially a modified F-104 with a wide-span, high-aspect ratio wing. Though it lost out to the Bell X-16, Kelly Johnson wasn't about to quit. Over the years, he'd gotten to know a lot of people in high places, and he developed consummate lobbying skills. With a revised design and promising an airplane within just 8 months, he got the go-ahead to produce 20 aircraft for $22 million. The project, codenamed Aquatone, was directed by the CIA's Richard Bissell, who found the Skunk Works' streamlined, informal method of getting things done much to his liking. Secrecy limited access to a mere handful of CIA and Air Force personnel, which was fine with Johnson because it freed him from a lot of needless paperwork and interference. The urgency of the project also freed him from what he regarded as the tyranny of technical specifications. His customers simply wanted an airplane that could do the job, and all he had to do was deliver on time. While the article, as it was called, was a relatively conventional design, the extreme altitudes at which it was supposed to operate imposed severe demands. Forced to ruthlessly cut weight, he reduced structural components to the minimum and designed delicate, glider-like wings spanning 80 feet and weighing less than 4 pounds per square foot. The fragile airframe was designed around a special high-altitude version of the J-57 engine, virtually hand-built to extremely high tolerances and originally producing 10,500 pounds of thrust. When the disassembled aircraft was unloaded from a C-124 at a remote desert test site in July of 1955, Johnson had met yet another seemingly impossible deadline. After reassembly, it was rolled out into daylight for the first time and painstakingly prepared for its taxi tests. On August 1st, as he had so many times in the past, Tony LeVere climbed into the cockpit. During his third run that day, he suddenly noticed that he was more than 30 feet off the ground. Coming down hard, the tires blew and the brakes failed and caught fire. Reporting afterwards, he explained that at 70 knots, I became aware of being airborne, which left me with utter amazement, as I had no intentions whatsoever of flying. Those fragile wings had more than enough lift. He completed the first real flight 4 days later, and on a subsequent flight reported that the aircraft climbed toward the heavens like a homesick angel. To conceal its true purpose, the Angel was given the misleading official designation U-2, and a cover story was released to the effect that it was being developed as a high-altitude research vehicle for the National Advisory Committee for Aeronautics. While it would perform this role admirably, tests focused on preparing the U-2 for its real mission, to carry 700 pounds of high-resolution camera equipment up to altitudes then beyond any air defense capabilities. And in July 1956, just 11 months after first flight, it commenced its clandestine operational career. Climbing to well above 70,000 feet as fuel burned off, the U-2 successfully completed flights over denied areas and brought back the first hard data on the status of Soviet military preparedness and the true extent of its intercontinental ballistic missile program. Called the Dragon Lady by its pilots because it reminded them of the beautiful, mysterious, and sometimes treacherous character in the Terry and the Pirates cartoon strip, it flew with virtual impunity for 4 years until that day in May of 1960 when Francis Gary Powers was shot down by a surface-to-air missile. While deep penetration of Soviet airspace came to a halt, the U-2 continued to overfly hotspots around the world, such as in 1962, when it confirmed the existence of missile launch sites in Cuba. And it would also continue to perform an incredibly wide array of extremely high-altitude research missions. Kelly Johnson had reason to be proud of his Angel. The Skunk Works had finally been formally established as Lockheed Advanced Development Projects, and on this, its first production program, he'd refunded $2 million from the original $22 million contract and built an additional 5 airplanes out of spare parts. Surely one of the best bargains in defense procurement history. That pride was rekindled when in 1981, the larger, more sophisticated TR-1 was rolled out years after U-2 production had ended. It was the first time the Air Force had ever put an aircraft back into production. And it remains to this day the highest flying single-engine piloted aircraft in the world. Back in December of 1956, the SkunkWorks' remarkable performance on the U-2 had convinced Lockheed to give Johnson the job of designing and developing prototypes for a small military jet transport. Dollars were scarce, competition keen, and he'd only have 8 months to do the job. Being on time had always been one of his cardinal rules, and in just 241 days he delivered the Jetstar. He'd actually been working on designs for a large jet transport since 1944. This trim little craft was actually a scaled-down version of the L-193, an innovative 1953 design which the airlines had feared too risky to support. Johnson, who continued to put in long hours as a flight test engineer on this project, was out to prove them wrong. And he was more than pleased with the results. A top speed of over 600 miles per hour, a peak altitude of 52,000 feet, and with wing tanks, a range of over 3,000 miles. The Jetstar easily won the competition, and though only a limited number went into military service as C-140s, ultimately more than 200 were produced, and a great many of them remain in service to this day. The Jetstar was a pleasant diversion as he worked on another, much tougher project. Even as development of the U-2 was still underway, he'd projected that air defenses would catch up with it within 2 years, and he'd initiated a remarkable series of design studies for a liquid hydrogen-fueled supersonic successor capable of climbing above 90,000 feet. Performance varied from Mach 2.5 and a range of 2,200 miles to Mach 4 and 9,000 miles. Because of the extremely low volumetric density of liquid hydrogen, however, the latter speed and range capability could only be achieved by building an airframe twice the size of a B-52. That was far too costly, and thus a much smaller design at the lower end of the performance spectrum went into development as the CL-400 in 1956. Though the CL-400 proved the technical feasibility of a liquid hydrogen-powered aircraft, Johnson was dissatisfied with its short range and convinced that the problems of producing and transporting fuel around the world were insurmountable. Refusing to build an airplane he didn't believe in, he recommended cancellation of the project in 1957. But he had an ace up his sleeve. As concurrent with the liquid hydrogen studies, he'd also examined the potential of another advanced design, using jet fuel, which at some loss in altitude promised Mach 3 cruise and 4,000-mile range. It was the genesis of his most spectacular creation. Given approval to proceed, in April of 1958, Johnson began a series of design studies, unveiled publicly here for the first time, for what he initially called the U-3, and then the Archangel, because it would soar much higher than the U-2. He explored various means by which he could get the vehicle to altitudes as high as 150,000 feet, employing a variety, or even a combination of rocket, ramjet, and turbojet power plants. At one point, he looked at the use of balloons to lift it to its rocket boost phase, and then at using a modified U-2 to tow a ramjet vehicle to 60,000 feet for engine ignition. He even considered a multi-staged vehicle, and one with inflatable wings and empennage. And throughout, he was challenged by the urgent need to reduce radar cross-section. For the first time, stealth would have to be designed into the airplane. The intense design gestation process was completed in just 16 months, and when he presented his 12th concept to the CIA and Air Force in August 1959, he got the go-ahead. When the stunningly beautiful A-12 was finally rolled out for its initial tests in April 1962, it wasn't some fantastic, multi-staged aberration. It was an honest airplane, but nothing like it had ever been built before. Ironically codenamed Oxcart, and designed for sustained Mach 3.2 cruise at altitudes between 75 and 95,000 feet. It posed by far the greatest challenge of Johnson's career, as everything from structural materials to hydraulic fluid and fuels had to be invented from scratch. For example, because of the intense heat at sustained Mach 3 speeds, averaging more than 550 degrees on the surface of the airplane, Johnson employed a titanium alloy for more than 90% of the airframe. But no one had ever before attempted to process such quantities of the extremely hard metal to the purity and strength levels required. And thus new forging and milling processes had to be invented and perfected. When the thin titanium skin on a wing panel shriveled up during heating tests, Johnson separated the panels from the wing spars with extrusions and put the now famous corrugations in the skin. When heated thereafter, the corrugations merely deepened a few thousandths of an inch and on cooling returned to their original shape, a common-sense solution to a difficult problem. There were literally thousands of such problems to overcome, and as always, Johnson stayed on top of all of them, looking over people's shoulders and asking lots of questions, always the best way, in his view, to get people to solve problems. And he continued to amaze everyone with, for example, on-the-spot predictions of skin temperatures, which after hours of calculation they'd find were within 1 or 2 degrees of the exact figure. The whole effort, completed in absolute secrecy with an incredibly small group of people, was all the more remarkable because it was done without the benefit of computers. As Johnson later recalled,
when you think back to 1958, when the basic design work on the prototypes for this airplane was being designed and built, we had to make use of the Michigan computer, which is a 12-inch slide rule, and it did its job quite well.
All of this prodigious effort was about to come to fruition when on April 25, 1962, preparations for high-speed taxi and an initial brief liftoff were completed. But as Lou Schock sped down the runway, he encountered nose-wheel steering problems and had to kick in heavy right rudder. Then, as Johnson wrote in his log, the aircraft got off the ground, and there was an immediate change of rudder angle. This set up lateral oscillations which were horrible to see. Schock was lucky to get the airplane back on the ground. The problem was fixed post-haste, and the next day he completed the first unofficial flight with the gear down. On April 30th, Johnson was back with an entourage of VIPs for the official first flight. Looking like he didn't have a care in the world, he offered a few last words of encouragement and advice before Schock taxied out. And from there, everything went flawlessly. "59 minutes later, Schock was back on the ground, welcomed by an elated Kelly Johnson and the small, awestruck assembly who just witnessed something very special. Limited by interim J-75 engines, the A-12 didn't begin to realize its full potential until after the Pratt & Whitney J-58s for which it was designed finally arrived in January 1963. At 32,500 pounds of thrust, the J-58 was every bit as exotic as the airplane itself. In combination with an extremely complex inlet and exhaust ejector system, it operated as a normal afterburning turbojet up to speeds of about 1,600 miles per hour, and then shifted to bleed bypass cycle, with the inlet actually providing most of the thrust at Mach 3 cruise. When a two-seat trainer became available in early 1963, Johnson, true to his convictions about flying his own aircraft, jumped into the rear cockpit, and, taking control after climb-out, he'd fly supersonic for the first time in his life. During the course of the test program, a pair of airframes were modified for a highly unconventional mission. In 1964, the Skunk Works built a small, 42-foot-long airframe with the very same materials used on the A-12. Designed to overfly areas deemed too risky for air crews, the D-21 drone would ride piggyback atop an A-12 for Mach 3 launches at 80,000 feet. And powered by a ramjet originally developed during the X-7 program, it would be even faster than the A-12. The finished article was mounted to its mothership, now designated M-12, in December 1964. And on December 22nd, the unusual pair taxied for the first time, and flight tests got underway. After takeoff on launch missions, the M-12 climbed to a rendezvous with a KC-135 for refueling, and then proceeded on to the predetermined launch point, where the backseater would monitor the systems and initiate the launch procedures. While there were several successful tests, it was always a very risky business at best, and Kelly Johnson personally canceled this program after a fatal mid-air collision in 1966. By then, however, he already had two other very successful ox-cart progeny off the ground. The first was the YF-12A, prototype for a proposed high-speed interceptor. It was this aircraft which went on public display when in 1964, President Lyndon Johnson announced the existence of the A-11. And it subsequently put on a dazzling show, as in May 1965, it claimed no less than 9 world records, including a top speed of more than 2,000 miles per hour and a sustained altitude of over 80,000 feet without in any way taxing its full potential. The YF-12 was equipped with an advanced ASG-18 Doppler radar system and configured to carry 3 AIM-47 missiles internally. Though missiles had never before been launched within the YF-12's speed and altitude regime, the aircraft and its systems scored a reported 90% kill rate, even against drones flying head-on down on the deck at distances of 120 miles and more. The Air Force was impressed enough to order 93 of the big fighters into production for the Air Defense Command, but budgetary constraints ultimately resulted in their cancellation. And shortly thereafter, the A-12 was also removed from service, leaving only the Air Force's SR-71, which took over its reconnaissance mission. Though everything about it and its activities would remain cloaked in a heavy shroud of secrecy, this was the aircraft that everyone came to know as the Blackbird. The solid coat of black paint, which seemed to add to its allure and mystery, actually had a very practical purpose. It reduced skin temperatures by about 75 degrees. Its clean, elegant lines and the smooth contours of its blended wing-body shape give the impression that an artist had sculpted it into a rare work of art. In aircraft design, however, more than any other field, form follows function, and here again, every line, every detail of the airplane exists only to serve some practical purpose. The chines, for example, which extend from the wing to the nose and flow gracefully up into the fuselage, actually satisfied a number of requirements. Aerodynamically, they reduced drag and added lift while also enhancing the stability of the aircraft. The SR-71's mission was long-range reconnaissance, and its fuselage was essentially a big fuel tank, and thus the chines also served to house its sophisticated cameras and sensors. Finally, those sloping contours extending up from the chines enhanced the airplane's survivability by reducing its radar cross-section. Thus, while an artist might envy its striking beauty, an engineer would only marvel at the logical genius of its design. That genius was recognized when, in 1964, Kelly Johnson became the first person ever to be awarded a second Collier Trophy. The SR-71 went on to claim the world absolute speed and altitude records, and then repeatedly extended them. And to the public, It always remained Kelly Johnson's mysterious, record-breaking Blackbird. The crews who flew it, however, had another name for it. Throughout its long operational career, it remained invincible and incredibly effective. And to its crews, it was Habu, dark-skinned pit viper with a deadly bite. And though it was finally retired from Air Force service in 1990, Kelly Johnson's Mach 3 masterpiece is still charting the future, its crews still looking up toward the blue-black void of space, flying exotic research missions for the National Aeronautics and Space Administration. When he retired in 1975, Kelly Johnson had been on the cutting edge of an advance from 200 to more than 2,000 miles per hour. He'd been involved in the design of 44 different airplanes, many of them among the classics of aviation history. And at the time, he was still looking very much into the future. He'd gotten the Skunk Works into a project which would bear fruit in the F-117A, the world's first true stealth aircraft. And he'd left a legacy which would leave its mark on the future. It seems kind of ironic that a lowly creature, known primarily for its odoriferous emanations, had, by the time Kelly retired, become a universal symbol for excellence. What was his secret? Well, he had a remarkable capacity to take a complex problem, reduce it to its simplest components, and then take the most direct and sensible approach to its solution. Always a maverick, he was smart enough and tough enough not to follow the committee rule of conventional wisdom. This gave him remarkable freedom. With that freedom came a tremendous burden of responsibility. Finally, and most important, he understood himself well enough to realize that with a few good people, you can do remarkable things. Kelly Johnson's greatest legacy wasn't just what he did, but the way he did it.
He decided he wanted to design aircraft when he was 12 years old after reading Tom Swift and his airplane. He designed his first plane before he'd ever seen one in person. When he first applied for a job at Lockheed, the company turned him down flat. He got his master's degree in aeronautical engineering and returned, and was rewarded for his persistence with an $83 a month job as a tool designer. By the time his career at Lockheed ended 47 years later, he had built the most important aircraft research and design facility in the world. There, in Lockheed's legendary Skunk Works, he and the team he led revolutionized aviation. For 30 years, it was impossible to see a significant display of American aircraft without seeing something Kelly Johnson had designed. Whether it was a fighter, bomber, transport, passenger liner, or even a spy plane, the odds were that he had designed at least part of it. Without question, he is the greatest aircraft designer in history. He is Clarence Kelly Johnson. Clarence Kelly Johnson was born in the town of Ishpeming in Michigan's Upper Peninsula on February 27, 1910. The son of Swedish immigrants, he got his Irish nickname from schoolmates after he stood up to the school bully.
He had been dealing with some of the kids at the school calling him Clara, since his first name was Clarence. And he finally had his fill of it and decided to take reprisals on one of the bullies. And after he was finished, the kids in the schoolyard decided that he could no longer be a Clara, and instead they were going to find some more appropriate name. And since Irishmen were known at that time for their pugilistic skill, they decided to dub him Kelly.
He designed his first airplane, which he called the Merlin Battle Plane, as a 12-year-old, and it won him a prize at school. He knew then that was what he wanted to do with his life. He paid $5 for his first flight, a 3-minute trip in a biplane that ended badly when the plane's engine conked out at 700 feet. When he got older, he worked in construction and in the Buick factory and saved his money. He took his savings to a flight school and asked to be taught to fly. The flight instructor, a cash-strapped barnstormer, refused Johnson's money and told the young man to spend it on college. Johnson enrolled at the University of Michigan just before the stock market crash in 1929 and supported himself washing dishes in fraternity houses. As an assistant in the aeronautical engineering department, he worked with the school's wind tunnel. The school allowed him to rent the tunnel out when it wasn't in use. Johnson charged $35 an hour and helped design a new, streamlined Studebaker model. He graduated in 1932 and tried to enlist in the Army Air Corps, but was refused. He returned to Michigan for his master's degree and, among other things, used the Michigan Wind Tunnel to help design aerodynamic racing cars for the Indianapolis 500. In 1933, he went to work for Lockheed in California as an $83 a month tool designer. Lockheed at the time was a deeply troubled company. It had just emerged from bankruptcy and had bet its future on the Electra, a 2-engine transport. When Johnson arrived in Burbank, his boss asked him what he thought of the plane. Johnson looked and said it would be unstable and that he did not trust Lockheed's wind tunnel tests. Chief Engineer Hall Hibbard sent Johnson back to Michigan with a model of the Electra and a mandate to do his own study in his own wind tunnel. "See if you can do better," Hibbard told him. He did. After 72 tunnel tests, Johnson came up with a newly designed flap system and traded the Electra's single stabilizer for a twin tail. Those changes stabilized the Electra and helped make it one of the most successful airplanes of its time. Johnson returned to Lockheed a full engineer. Assigned as the Model 10 Electra's flight test engineer, he at last started flying on a regular basis. He befriended Amelia Earhart and advised her on several of her missions. She flew an Electra, and Johnson advised her on techniques of fuel mixing to help her get the best performance out of her plane. He continued to work on updates to the Electra through Electra Model 14, and was soon attracting attention outside of Lockheed. In 1937, he won the Sperry Award for outstanding achievements in aeronautics by a young man. That same year, Congress passed the Neutrality Act. That law was designed to keep the United States out of World War II. At the same time, those in the military had become convinced that American involvement in the war was inevitable. They threw as many of their precious dollars as they could into the design of new equipment. Lockheed won the competition to build a new fighter with a plane designed by Johnson, the XP-38. With 2 engines and a double fuselage, it was an unconventional aircraft that had its share of problems. In particular, its high speed and tight maneuvering sometimes created forces so great that they shattered the plane in midair. Once again, Johnson went back to his wind tunnel, and after making a few changes to the plane's design, it passed Army Air Corps muster and was ordered into limited production. Johnson, the designer, was 27 years old. In the late 1930s, Lockheed came back from bankruptcy largely on the strength of its commercial aircraft. The Electra in particular had built a profitable customer base. But if Lockheed was going to grow, it was going to have to build a successful military aircraft business. The P-38 was a start, though when the Army Air Force first awarded the contract, no one knew how many thousands of planes would eventually be built. In 1938, with Europe on the brink of war, The British sent a purchasing commission to the United States in search of military aircraft, particularly a long-distance coastal patrol bomber that could be used to hunt submarines. The commission, scheduled to visit several aircraft manufacturers, did not originally intend to visit Lockheed. Their schedule changed at the last minute, and Lockheed was invited to make a presentation, with only 5 days to prepare. During the 5 days of preparation for the Brits, Johnson showed what he was destined to become famous for: the ability to make something entirely new out of existing components, and to manage a project to completion with a ruthless eye to the deadline.
He himself lived by the credo, be quick, be quiet, be on time. He was somebody who believed very much in getting good people and giving them the ability to do what they do best. He also believed in minimizing the number of people working on any one project.
In only 5 days, Johnson and his crew not only redesigned the Electra to fit the needs of the Royal Air Force, they also built from scratch a full-scale wooden model of the plane, a civilian transport converted into a medium bomber. The Brits were amazed. They were so impressed by Johnson and his crew, they invited Lockheed executives to England to confer with the Air Ministry. Johnson went along. At the meetings, the British changed the design specifications, necessitating a complete redesign of the aircraft. Johnson locked himself in a London hotel room and in only 72 hours completed the engineering drawings. The British were, once again, amazed, and Lockheed got the contract. But not before the British expressed their hesitancy about working with an engineer as young and inexperienced as the 28-year-old Johnson. Lockheed reassured the Air Minister, who ordered 200 of what became known as the Hudson bomber. It was the largest single order of aircraft ever received by an American manufacturer, and upon the party's return to the United States, Lockheed promoted Johnson to chief engineer. In 1939, the Congress significantly increased the defense budget, and P-38 started rolling off the line in record numbers. During this period, Johnson truly mastered the art of manufacturing, streamlining production processes, and developing an entirely new job, the program manager. Now a staple of manufacturing, the program manager is a person far down the chain of command who has working control of a project. If that all seems a bit heavy on the business administration in a discussion of aircraft, consider this. Johnson believed that outstanding aircraft designed and manufactured quickly were inevitably the product of a single visionary. That visionary was usually, of course, Johnson.
He was not someone who believed in development via committee. He was also somebody who hated lengthy reports and normally limited any report that was sent to him to 20 pages. He believed in brevity, he believed in clarity, and he believed in giving people the tools necessary to get the job done.
In 1943, Lockheed put Johnson in charge of advanced products research, setting him up on a plot of land on the outskirts of Burbank, California. Johnson called his new kingdom the Skunk Works, after the still in a cartoon strip, Little Abner, that was responsible for the making of a mysterious and powerful brew called Skunk Works.
In the Little Abner cartoon, there was a potent mystery elixir known as Kickapoo Joy Juice. And Kickapoo Joy Juice was made at the Skunk Works, or SkunkWorks, as it was called in the comic strip, through a variety of things that were thrown into a giant mixture, among them skunks, old shoes, and things like that. And the nickname was applied to the Lockheed operation because, indeed, it was a mystery elixir. Nobody was quite sure what was going on in there, but they knew that a lot of things were being thrown into it and that Kelly Johnson was pulling a lot of people from various locations in order to create something interesting.
The job of the Skunk Works was to quickly, cheaply, and secretly develop advanced aircraft that could help win the war. Its first assignment was the P-80 Shooting Star, the first American jet. Intelligence had determined the Germans were far along in their development of jets, and the not-so-secret fear of the Army Air Force was that the Nazis would deploy their jets in large numbers before the war in Europe had ended. The effect on the Allied bombing campaign would have been horrendous. The Allies' propeller-driven fighters would have been almost useless against a jet-powered fighter.
Kelly Johnson, in his efforts to oversee those operations, would pull people from other projects and would go about trying to get a minimum number of the very best people and put them on the project, give them minimal supervision, but let them trust them to be able to do the jobs that they're chosen to do.
After setting up the Skunk Works and recruiting his team, Johnson went to work on the P-80. Lockheed's contract with the Army Air Force gave him an incredibly short schedule, 180 days. Johnson went on a binge of designing and set his team to work on various critical paths and had the prototype ready for testing 37 days ahead of schedule. In 5 months, Lockheed had designed and built the first American jet. They hauled it from Burbank to Muroc Air Base in the California desert for testing. Fearful that there might be spies in the surrounding hills, they disguised the jet during transport with a plywood propeller. Johnson said years later that when he rolled out a new plane for testing, there was only one thing he thought about. What have I forgotten? In the case of the P-80, despite the short design and construction cycle, he hadn't forgotten much. It was a beautiful aircraft, faster and more agile than anything in the American arsenal. The war ended before it saw combat, but it evolved into the T-33, one of the best and longest-lived jet trainers in history. When the war ended, however, there were those who questioned whether the Skunk Works had a role to fill. After World War I, the business of aviation had shrunk almost to non-existent. After World War II, many people expected that it would again. But there were two basic differences between the ends of the wars. First, the United States was engaged in the world after World War II in a way it wasn't after World War I. No one could reasonably expect the world's only nuclear power to go back into hibernation. And second, before the war ended, it became clear that the post-war world would require a strong and ready military. Because on the day the Japanese surrendered, the world separated into two groups of allies, those in the communist East under the control of Joseph Stalin, and those in the democratic West. World War II was over, but the Cold War was just beginning. Kelly Johnson and the Skunk Works were just about to become the most important aircraft developers in the world. Over the course of his career, Kelly Johnson designed more than 40 aircraft. His most prolific period by far was in the 1950s. That was a decade of tremendous technological advance, achieved in an atmosphere of never-ending crisis. And there was no better place for aeronautical engineers to work than the Skunk Works. Johnson designed and built the Constellation, the most elegant aircraft of its time, and a plane that served effectively in both civilian and military roles. He experimented unsuccessfully with vertical takeoff and landing aircraft, with the idea that they could operate from relatively small ships. He designed the F-104 Starfighter, at 1,300 miles an hour, the fastest aircraft ever flown at the time. It was a sometimes fussy plane to fly, and at more than Mach 2, there wasn't a lot of room for error. It was adapted around the world to a number of difficult tasks, including carrying nuclear weapons. Johnson didn't approve of all the modifications others were making to his plane, but could do little about them. As the Cold War heated up, it became clear that the United States needed a way to peer deep into Russian territory. East of the Ural Mountains, where the Russians did their atomic research and where they developed their aircraft and missiles, the United States didn't even have an accurate topographical map, let alone a way of getting information on military capabilities. The Air Force put out a quiet request for a fast, high-altitude plane that could overfly Russia and bring back pictures of the communist secret bases. Johnson at first toyed with modifying the F-104, but it lacked the range and would be too difficult to fly on long missions. In 1954, he sent the Air Force a proposal to build a plane that could fly at a range of 4,000 miles above 70,000 feet. It would be slower than the Air Force had hoped, but at that altitude would be high above Russian air defenses. The Air Force didn't believe Johnson could do it. They doubted any jet engine would work at that altitude, and instead ordered a competition between manufacturers for the best biplane design. President Eisenhower approved a $35 million contract with the competition winner. Johnson and his Skunk Works team went into overdrive. In mid-November 1954, he met with the government advisory board on what was then called the CL-282 project. 10 days later, he formed the team to design the craft. On December 2nd, the first 12 engineers went to work designing the aircraft systems, and the first design drawings were completed and released to the shop for manufacture the next day. A week later, the drawings were complete, and by the end of the year, he'd won the contract and frozen the design. Wind tunnel testing completed in March, the first plane finished in July, and the first flight took place on August 4th, 1955. In less than a year, from pipe dream to first flight, Kelly Johnson and the Skunk Works had designed and built a completely new kind of airplane. The U-2 had something of a patched-together quality, to be sure. The first ones cut weight by leaving out the ejection seat, and the balancing wheels on the wings dropped off at takeoff to lose a few more pounds. The engineers were still making modifications on the craft in the summer of 1956, when a young pilot named Francis Gary Powers saw his first U-2 parked on a taxiway at a secret base in Nevada. It had not been built to last, he said years later. Powers was among the pilots who flew spy missions over the Russian heartland in the U-2, and for years it was safely out of range of the Soviets. The planes routinely returned with photographs showing Russian fighters 4 miles below them, coming up for a fight but unable to fly high enough to get a shot off. Eventually, however, the Russians improved their air defenses, and by the time Powers was shot down in 1960, Johnson was already at work on his next-generation spy plane. Johnson, with the U-2s flying with seeming impunity, had gone back to the government to propose a plane that could fly 10,000 feet higher and 4 times as fast as the subsonic U-2. Building a plane that would cruise at Mach 3.2, Johnson said years later, was the hardest thing the Skunk Works ever did. Everything about the plane, Johnson said, had to be invented. In 1960, the Air Force gave the go-ahead for Johnson to develop the A-12, a plane that didn't succeed as an interceptor, but paved the way for its slightly larger sister, the SR-71 Blackbird. Built out of titanium, which is light and could tolerate the 500-degree temperatures that built up as the plane sliced through the atmosphere at more than 3 times the speed of sound, the Blackbirds were like something out of a science fiction movie. The rollout was Johnson's proudest day. It was, he said, the smoothest test flight he'd ever been through. Johnson, who had never been much of a talker, insisted that he was not bothered by the fact that he couldn't talk about his perfect airplane. If I can talk about it, he'd like to say, it's obsolete. But years later, when word of the SR-71 had leaked out and the Air Force had stopped denying its existence, he took joy in its racing from New York to London, a distance of almost 3,500 miles in less than 2 hours. And before the Blackbirds were retired in March 1990, an SR-71 flew across the United States coast to coast in 68 minutes. Kelly Johnson retired from Lockheed in 1975. Even then, he was a presence at the Skunk Works. His 14 rules of effective program management are gospel there and are taught in some of the leading business schools in the world. Johnson even consulted with Lockheed during the development of the F-117 stealth fighter. As an old man, he said that there would come a time when aircraft were no longer relevant. People wouldn't travel for business, he said, because they could sit at their desks and talk to people in Europe by video phone. And on the battlefield, manned aircraft were no longer cost-effective in an age of missiles. Though it hasn't happened yet, don't bet against it.
I think his greatest contribution was in the vision that he had for the Skunk Works, for Lockheed, for American aviation, and in his ability to translate that vision into something that other people embraced and believed in and wanted to work toward. To a great extent, his greatest contribution was his ability to get other people to commit to his dream.
Kelly Johnson died just before Christmas in 1990.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunk Works Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.